we come for the field, when the field geologists come, they got the core, pick the core in the pad, the drilling pads, and we got the core obsidian. That's the first step. We downloaded the rock and get that. For what, Mike?
Depths and the box number, the interval, and then we clean the core just to make sure it's nice and clean, because we do a quick log of this just for purposes of daily reporting, a quick summary. And we also put the information for the next step, which is core photography, of what the box number is, what the meter interval is represented in the core box. So from here,
you just started then.
yeah, right. Yeah, it's very short. It's only 20 meters deep. So it's, you can see how broken up and oxidized it is because we're so close to the surface. There's a lot of surface weather.
This is the number of the
As you get deeper, you don't see all of these brown stains, which is basically oxidation of sulfide, and it looks cleaner. Yeah, it's really soft. It's deeply weathered rock, and we're not going to see any significant mineralization in this. And if there was copper at this shallow interval, it would have been washed out and concentrated down deeper. So the core comes from the field like this. We start the process, we label the boxes, because the next step is going into core photography for documentation.
Please, ¿puedes venir tantito? And we can translate it, try to translate it. She's in charge of these activities.
Una vez que se lava y se mide, lo que hacemos es traer la caja, se coloca ahí en el rectángulo, se toma una foto en seco y una en húmedo.
Okay. So they bring the core box in here after the notes are taken, the quick log is done, and everything has been noted and measured outside. They bring it in here, put it on the floor, they have a standard camera mount right there with standard illumination, so it always is the same interest on how the appearance is. And they photograph it both wet and dry, and that documents it. And then from there, it goes to her department, which is the geotechnical one. And then she always cleans the Orocos.
I like this.
Oh yes, we have a standard picture, the quality standard. We got this wet sample and
Standardized.
We have a very cool guy usually.
And so every box gets photographed wet and dry. Every photo is archived so that it's thoroughly documented. It all gets immediately.
Why do you photograph it?
For documentation, because one of the things that we can do with the photographs, if there's any question regarding alteration, geology, or structure like faults and fractures, we've got that documentation to go back and compare to the logging that's been done to verify that it looks correct. So a geotechnical engineer is part of their habit, like me being a QP for a project. I can't work on a project unless my boots are on the ground. I have to go there. And so a geotechnical engineer is going to look at the geotechnical logging, compare it to some of the photographs to make sure it looks right. We record all of the data into a standardized format with drop-down windows where we can record all the features of the fractures and breakage in the rock that occurs as we log it. And all of that is primarily done for purposes of geotechnical engineering. That is, when we design a pit, if we design the pit and we don't have geotechnical data, we would try, the high walls of the pit would tend to be flatter. If we have geotechnical data, we can steepen it up in places, which reduces the stripping ratio, which increases the economics of the project.
First step, she was, as soon as she got the core boxes here in place, he just marked with the color every single fracture. Natural fracture, we have mechanical fracture made by the driller. We have to distinguish what, separate what.
Todas las X son fracturas que son creadas por el humano.
That's a mechanical fracture done by the driller. This is the X number. And the blue one is the natural.
Y las que son paralelas son creadas por la máquina al perforar.
And some with the drilling process, sometimes the rock is broken, but she's doing a very good job because she has to make a difference. Yeah, which one this is. And it takes a while. She has a lot of expertise. All these fractures, she's using this tablet and collecting the data in this way. finalize with the geotechnical logging. They move the boxes to the other part of the core shack, and where we going to start collecting the structural data, and as well as geotechnical, geological logging, core logging, basically. You know what we want to distinguish the lithology, fracture structures. He's the structural guy. He's going to talk about it. Platícales qué es lo que tenemos.
Yeah. Well, after the geotechnical department finishes with the description, it goes to the geological logging and also to the structural department. So we are especially identifying the major structures in the structural and characterizing the mineralization trends. That is the main thing of the work that we are doing, because it's important to know which geological structure, which discontinuities are acting as a structure to conduct the fluids that bring the copper to the surface. So that is the job that we are doing.
They collect the data to provide with a model, try to understand the structural model for the property. We have a lot of knowledge right now, but I think every day is improving. And the idea is to collect the data and use this information to get a better understanding of the deposit, you know, and try to find the places where we get the best copper numbers. Yeah.
He is a logger. He's in charge of this hole. So we're just trying to describe all the lithology tab, and it's divided into 5 tabs here. We are using now Logchief software. First we start with the lithology tab, and then minerals, alteration, veining, and structure. So we have one guy here that is in charge of structure, this is Fidel. So he's filling all the boxes in the lithology first, and he's describing the hole before the seamless. So we are finding some nice veinlet here, some good structures. We are now so far until 500 more or less. So yeah, if you want to see.
It would be very good if you would.
So why are you watering it?
It's easier to see the minerals. See how it's easier? It's harder to distinguish the different colors and the different grains here. If you wet it, it's just easier to see. Watch what happens when I wet it. Go ahead and punch it. It jumps out. So we look at it 2 different ways. It's just easier for me, certainly, if the sample is wet, to understand what I'm seeing. And so with this, you can see right there, there's a big thick vein of sulfides. Pyrite.
And over here the fractures. Yeah, there is lawsonite. It's a bunch of that veinlets with big halos that contains more here.
And just very briefly, just point to and show the kinds of things we're altering. We're logging. Fractures, contacts, alterations, silicification, potassic alteration.
Briefly, for example, this is quite fresh rock, so this is the first thing that we need to observe. And then structures like veinlets, for example, like that. And also, what is the amount of sulfides that we have in any structure. Specifically, we look for the set of veinlets. So we describe them as a group, and then we count one by one and see what is the density of in each interval of the lithologic unit.
And you can see some things here. There's tourmaline.
Tourmaline.
It often occurs with the mineralization, with the potassic alteration. This is a rock that is fairly well silicified, and you can see this gray area through here, like in here. These are dominantly quartz veins, and most of the copper and molybdenum mineral is associated with quartz veins and other features like that that we see in the rock. So they're logging all of these differences that you see that are based initially on the lithology. The pink minerals there are potassium feldspar. A lot of the black areas that you see in some cases, probably up in here, is potassic alteration with biotite. So we're logging all of these different features in the rock. And all of that data is collected and put into Leapfrog so we can develop a three-dimensional model. And we can look at the distribution of all this. So why is this important? Because it helps us develop that restriction on where is the ore on a geological basis. So we're not depending purely on copper assays. We have geological controls in order to result in a better resource model down the road. It's all towards the economic geology is what we're focused on here now.
After the logging part, we started with the sampling. We prepare a list of each interval that we have to send to the lab. So in that case, he prepared an Excel file with one interval each 2 meters. So this is the parameter that we have for the sampling in all the holes. So for example, let's say if we have 498 here, the sample should be until 500, right? So all the intervals should be packed in the should be sent to the cutting room. Yeah, and then so they will prepare everything, cut the samples, and put in the box. And yeah, and in that area, there is one person who is in charge of that, right? So we prepared all the sampling with the list and sent everything there for the QC control.
Well, in geochemistry area, we collect data with 2 equipment. This is a terrace bed halo. This collect data only mineral alteration. And
It identifies mineral species.
And this is the nitrogen. This collect elemental data.
We choose a spot and we try to start the reading. Sí.
And that instrument shoots out a little X-ray beam that makes the particular minerals give a response, a wavelength response back, so that we can look at how much of different alteration minerals are in the rock.
To have an idea, what is the variation of these minerals?
Okay, we show you muscovite, clinozoisite, muscovite is a mica, it's a alteration mica. The clinozoisite as well is another kind of mineral, alteration mineral. And we use this information to get a better understanding of what happens in the rock, the alteration, and what level of the mineralization we are.
This is useful for telling us about the mineralogy. It's a confirmation of what we observe with the hand lens and with our eyeball. This is a direct measurement using X-rays in order to tell us what the mineralogy is to confirm what we're logging. It also gives us information in more detail about sometimes there are minerals that occur that aren't obvious visually that we can pick up with that instrument. Very microscopic.
Do you do this on every single one?
Yeah. Every meter we take a reading of this. Just like we do with the other instrument, which tells us about the elemental distribution, this tells us about the mineralogical distribution.
Select a piece of core, you see the chalcopyrite. We'll get together what parts of the field. She is the expert.
She has the touch.
Zara with an X-ray gun.
The practice. Shoot the veinlet and shoot. This takes a little time, 50 seconds.
Oh.
Exactly.
So she's building up her strength in her arm.
But we can see the copper value, 1%.
1.1%.
1.67%.
1.67%. Of course, that's a high-grade vein. That's not typical of every place, but you can get some confirmation information about where high-grade veining is versus disseminated mineralization. Because one of the things that the geologists see here a lot too is that the chalcopyrite that contains the copper is very fine grained sometimes. It's hard to see sometimes, the grains are so small. And that relates back to the metallurgical testing that's been done where a relatively fine grind is needed to liberate the chalcopyrite so you can capture it in the flotation process of recovering the copper.
So 250 ppm molybdenum as well?
Yep.
It's finished?
Yeah, finished.
Yeah, so what does all of this mean?
Well, we have fierro,
Iron. Yeah.
iron, and then copper with 1.66%.
It's a really high grade number because dew is a very high grade vein.
Yes, then molybdeno,
Molly.
plomo.
¿Cuánto es molibdeno?
Molybdeno es poco,
Okay, just
2.42.
traces of moly, and we have some kind of lead. Some zinc. We have zinc numbers. No? This
So
is-
how is this one different than the previous two?
The previous tool just identifies minerals. This one identifies the amount of the elements that are in the rock. So minerals are made up of elements, right? So in some ways, there's some duplication. But for instance, one of the pink feldspars I was showing, with the other instrument, it would show lots of potassium feldspar. But if you measured it with this, it would also show a high potassium level. So one measures mineralogy, the other measures elements.
And you use both tools
Both.
for
We use both
for every
tools.
meter?
Yes.
I think
Very
we
well.
have
The instruments back up the observations of the geologists, and as we calibrate our observations, so then the geologists are able to make better calls going forward. But these are standard tools now in core shacks around the world, and they're unbelievably useful here.
The last holes that we have, let's say hole 13 and 14, 12 also. Especially in 13, we have a really nice zone with a well-developed veinlets that is classic seen in also another porphyries, for example in Chile or southern Peru. It's really well cooked. The intrusive that we have a little bit more that we saw it in the central part in Santo Tomas. But at least these well-cooked veinlets, it shows us that we are really, really close to the main zone or core zone that is classic mentioned in porphyry copper system and also molybdenum. But we have really well development of halo parallel to the mineralization that is clearly marked by chalcopyrite. We have realized that there is another kind of copper sulfide or oxide that we haven't seen yet. We are in progress to analyze which mineral is carrying out the copper, but still we have that we know that we have something else there that is carrying out the copper. So we don't know what's happening there. So, but at least we have the main zone very close in the hole 13 that it has at least more than 150, 200 with well-cooked mineralization in intrusive and the andesite also. I haven't thought that before. To be honest, the andesite was the less chance for me because the alteration that we have in that volcanic sequence, it doesn't contain too much in the classic system porphyry copper. But here it's a little bit strange because sometimes we have volcanic sequence with good mineralization, and we saw it in the lab results there. And in the hole A, for example, is a good one, right? So in that hole, the monzonite, that is intrusive, and the volcanic sequence is really well intercalated between them. So at least we could say that two pulses or two intrusive in this system could be carry the copper. Just in sulfides or oxides, we still don't know exactly which mineral is, but we will look for that soon by doing the petrography and mineralogy studies. We started with the lithogeochemistry to identify which monzonite is the best host for our system, and we will look for the fingerprints that is special for some porphyry copper. We were in touch with some guys that is specialists on that. They are working with a special software that is called IOGAS. This is a really helpful software. Of course, we need to add more variables, structural geology, lithology, that is the basic for us. As Mike said, most of the time the basic thing is it comes easily if you use it in the right moment. So we're in progress, and I think we are going good so far. At least in the last 12, the last holes 12 and 13, 14.
Is that the hole? Can we see the veins?
Yeah, at least in this part, we have exactly here one of the best zones. You could see in the potassic alteration. Cross-cutting veinlets. And this looks like also in Chuquicamata. Chuquicamata mine is one of the
Hold on.
biggest.
Chuquicamata is
Yes.
similar to Santo Tomas?
No,
Chuquicamata?
¿Tienes agua?
Oh, yeah.
¿Tienes agua? Okay.
No, it's okay.
Chuquicamata is one of the world's biggest copper mines.
Yeah.
By a
Yeah,
long.
I saw it many samples for that because we have realized some studies with fluid inclusions. We saw the bubbles of these veinlets in the microscope, and this is impressionable because it's impressionant.
Pretty impressive.
It's
Is
impressive.
this hole 13?
Yeah,
Yeah,
hole
hole
13.
13 is a
Yeah.
very good hole.
It's a really good hole because just with that volume of sulfide, it's enough to have at least 0.4, 0.45. Yeah, and it's quite similar. This is alteration. This is not a fresh rock.
It's
This is already altered.
alter rock.
Yeah, it's already altered by another fluids,
Yeah.
another
So
quite.
maybe two
It's
intrusions.
two
Maybe
stages
two
alterations.
structures. At least maybe two. And we need to do the lithochem to know
Tu lupa para
which.
que lo vea.
Yeah. If
You
want
can take a
use
look with
this one,
the lens.
you could see sulfides there.
Get close.
Well, I mean, this is some core we're just looking at here, and very exciting. We're getting sort of multiple veins, multiple mineralized veins.
What does it mean?
What does it mean? Basically, I mean, for a given volume of rock, more vein systems give you more minerals. So normally you wouldn't find this kind of rock and say this is ore, but with this kind of veining, this is economic.
The samplage.
Yeah, yeah.
Okay, at least with this kind of veinlets and alteration that we have in this rock, we could predict that we have 0.5, 0.55% of just copper, not equivalent, just copper.
And if we included the equivalent,
At least will be more, of course, 0.6, 0.62, something like that.
and that's hole number 13.
Yeah, and it contains moly, so it should be more.
So we use also the IQ, and we identify where we have major structures. For example, I brought this sample from other core, and we have a rupture here in this section. Then we use the IQ to measure the data and an Excel file. So when we find a structure like this one, we identify the depth of the structure and use the IQ to measure it. And then we measure the fault. So we have data, and we have the attributes of the fault, the tip, and the deep direction. So we can use that data to plot in some softwares in order to know how is this fault in the surface. And also we are measuring some structure that has mineralization. For example, we have this vein here. Okay, as you can see, we have mineralization focusing in one fracture that was filled with pyrite, chalcopyrite. So that is the main task of the structural geology department: identify the sets of fractures that are bringing the mineralization, because we have a strong structural control of the mineralization in Santo Tomas. So this is the main focus of the department. So once we have all the core, we analyze the major structures and also the mineralized structures, and we do this for all the core that we have. Then we have the data, the Excel data, and also the IQ data. So we can make a statistical analysis with those data in order to know how is the structural, the major structural, which is the behavior of them.
I'm going to bring them back because actually that's a really cool thing. So yeah, it's a structurally controlled deposit, right? And so understanding where the faults and major structures are going to help us understand where the mineralization is and have implications for the engineering. The data that you see on the screen, Fidel's screen there, that is a stereo net. It's similar to how we plot maps, right? Global maps. And what that is a look into the bottom of a bowl. That particular is a lower hemisphere projection. And each of those dots is a piece of paper, a plane. So I'll get you to hold the plane. So if you ever project that piece of paper, the plane with its dip and strike into the bottom of a bowl, and you put a pencil through it at right angles, it would intersect the bottom of a bowl with a point, right? So every one of those points is a discrete plane in space. And then what Fidel does is he contours that data, and then he tells us where the principal structures are. Yeah, we built a dedicated core cutting facility just to cut down on noise, both for all of us working here, but also because we've got neighbors just over the fence. So there is the likelihood we'll have double shifts at some point with a lot of drills turning, so we wanted to make sure we could control noise. And so in here, just a dedicated core saw facility, and it's kept secure. We don't sort of track visitors through here generally because of the security of chain of custody for sampling. But we'll fire up the saw and let you see how it gets.
Yeah, let's do it. Why you cut this?
We want to preserve some of the core. We have to do some check assays. You can see they did a half split and then a quarter split. Generally, we send off the quarter split for the assay lab, but we also do duplicates where we take in certain segments part of that quarter that's left over and send it to the lab too, because we're trying to see if they give us the same values. Again, it's kind of like the QA/QC procedure that we use with standards. We also do that in order to look at the variability of copper and molybdenum grades within the same piece of rock, because it isn't exactly the same. But if we understand that variability, it gives us more information about statistical modeling for the resource. So here, once the samples have been taken, they've been split and put into bags with all the protocols we follow. They get put here. So we put a bunch of bags together, approximately 10 samples. You can see in the gunny sack.
This is before they go to the lab or after they go?
This is before they go to the lab. They're securely stored here so that nobody can mess with them. And then the assay lab sends a truck to pick them up, and they pick up a couple hundred of these large bags in one shipment. And then the chain of custody gets handed over to the assay lab all the way through their procedure, and then eventually we get the coarse rejects and the pulp rejects back for additional testing if needed down the road. Any independent person or qualified person that might come here if they're interested in investing in the property, they might bring in somebody like me, a QP, and say, okay, I visited the property, boots on the ground, it looks real, and they'll take some samples, some of the cuts of some of the pulp rejects or quartz rejects that we have back from the lab eventually, and they may check some of the core samples that we have, the leftover pieces of quarter split core, and put it through their own lab that's also an ISO certified lab, and make sure that they can confirm that the values, the assays that we're using are trustworthy.